Hello, and first of all, thank you for watching my previous Jai video. It got a lot of views and a lot of feedback. Today, I wanted to show you how exactly Jai compiler compiles your program, how can you affect this process, why Jai doesn't need an external build system, and I will also address the most common technical question from the previous video. First of all, if you just type Jai, just call the compiler itself, you will see this. You need to provide an argument telling the compiler what to compile, sorry. And if you provide it with a file, main.jai, it will compile it. And it will show few interesting things. So first of all, there is some linker output, but then you will see stats for Workspace 2, aka target program. And then it will show the output. So what's that? If you grep for a part of the first error message that ended with sorry, you would actually see a hit, something in module's default Metaprogram. And indeed, if you go there and look around, you will see that if not printed help or printed version log, you need to provide an argument telling the compiler what to compile. So exactly the thing that Jai told us. And also, if you go at the very top and look at this, you would see a call to compiler create workspace with the name of target program. And as you can remember, here stats for Workspace 2, target program. So when you invoke Jai compiler, the first bit of, let's call it user space, that we control is called the default Metaprogram. It is the thing that the compiler calls to compile your Jai program. And it's all here bundled with the compiler. And you can actually modify it. For example, if you look for this line that says sorry, here it is, and you can just straight up modify it like this, say not sorry, and then if you go back and recompile, let's just call the compiler without an arguments, you will see that now it prints not sorry. Right, and if you go back here and rework the change and go to the very bottom, you can see this. This is Jai help string. So this is getting printed when you call Jai-help. And look at this, if I press Jai-help and press enter, here you can see this. Available command line arguments, blah, 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 blah. Here, all of them. So what this default Metaprogram does is it is using #run, which runs this build procedure at compile time. And inside of this build procedure, as I've already shown, a workspace getting created with the name of target program. And what is a workspace? A workspace is an isolated environment for compiling things. So you can spawn multiple workspaces in a way that lets you, for example, build a debug and release version of your program at the same time. Or for example, you can build a DLL and in a separate workspace you will build a program. Or for example, one of the use cases that I'm using it in one of my projects is I compile the main program and tests at the same time in two separate workspaces. And since workspaces are fully isolated from each other in a sense that they have independent imports, they have independent namespaces, independent types, you can compile them in parallel, which compiler actually does. And yeah, so this default Metaprogram, it spawns a workspace that switches to our code. And later it handles command line arguments that help string prints to you. So here is switch case and it handles like release, target architecture and stuff like that. And this is actually why when you compile the program, you can see that target program is workspace 2 and not first one. You probably guess it already why. Because the first workspace compiler creates internally for the default Metaprogram. And as a matter of fact, if you try to comment this build in a default Metaprogram and run the compile again, you will get this interesting error in workspace 1. Which is called first workspace. Build options output type set to executable, but blah, 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 blah. So yeah, first workspace is the default Metaprogram. which you can absolutely change to whatever you want. By the way, this is wild level of control. And the second workspace, the target program, is whatever we as a user of the compiler have control over in our own application. So in this case, we compile main.jai directly, so the second workspace will be here. So let's go back and uncomment this, and let's go back to our program. Hopefully it's clear enough. Compiler that calls default metaprogram. We can control default metaprogram if we want. Default metaprogram creates a target program workspace, and then we get to our own program. Now, we don't necessarily need to compile our program directly. We can have our own metaprogram, and usually people put it in files like build.jai or first.jai, in which you usually create a build procedure of your own that you will then run at compile time, just like that. And if you try to build it, so here build.jai, you will see this error in workspace 2, target program, which default metaprogram created for us. No program entry was found. The designated entry point name is main. So it runs this build script, but we lost our main.jai file, and now the compiler doesn't know entry point of our program. Actually, default metaprogram is structured in a way that lets us learn, and this is actually intentional. So if we go to build that is in default metaprogram, we can start stealing things from here. So for example, we need to create a workspace for our main program. So let's just copy, and for the sake of an example, let's call it somewhere differently. So just to clarify, workspace is just an integer, and this name is purely for login purposes. So you can have multiple workspaces with the same name, it doesn't matter. Let's call it my target program. After we created the workspace, we won't care about command line arguments, but we will get a build options for newly created workspace. So let's just straight up paste them here. And then on these options, we need to set few things. So for example, there is output executable name, and let's call it main. So this is literally a name of the file that compiler will generate. So main.exe, or just main if you're on Unix operating system. And if you search for this name in main metaprogram, here you can see that it gets set if -exe command line is provided. So this is how you can start writing your first metaprogram. You just open default metaprogram, it's 500 lines of code, a lot of it is text and some sort of documentation, so it is very easy, it is very simple, it is very descriptive. So you set your target executable name, after which you set build options. Set build options for our options, and you need provided a workspace, so W, for which workspace you set the build options. Because as I said, you can spawn multiple workspaces and each of them can have their own independent build options. After which you need to start adding files to the workspace. And this is where, so add build file. Again, we need to add it to the workspace, and here we can provide a name with the path. We can use a relative path because our build.jai is in the same directory as our main.jai. So, and we'll call it main.jai, just like this. And if we compile our program now, so we get a declared identifier compiler create workspace. This is because compiler create workspace comes from a module named, if you were the previous video, compiler. Yes. So Jai exposes a set of compiler functionality as a library. And now if we compile it, undeclared identifier log error, because log error is in basic. And now if we compile it, we still have no program entry was found, but note how it says that program entry was not found in workspace 2 target program and not my target program. So it tried to produce an executable for our metaprogram, and we actually don't want that. We only want to produce an executable for our main.jai file. And in order to do this, we need to tell the compiler that this workspace does not need an executable. So we need to set a build options, DC, which means during compile time. And know that here we don't pass a workspace because it expects to act on the current workspace. So we set do output equals false. And if we do this and we recompile, we see that our program successfully compiles, it prints hello Sailor Moon, and note how the stats are now for workspace number 3, which is called my target program. So these 10 lines of code is the minimal custom metaprogram. You can call it a minimally viable boilerplate to start customizing Jai build process. And Jai build system is written in Jai itself, which makes it very robust and super portable, and you don't need to learn a separate Turing complete language like in case of CMAKE, or some scuffed way to combine scripts like Make, or you don't need Ninja, you don't need Visual Studio solutions, you don't need anything. You just program in the same language that you use to build your actual program. And if we go and see build options, which is a struct that is actually also exposed in the compiler module, this is everything you need to customize your build process. As you can see, the output type, operating system, and there is a lot of stuff. So one interesting one is import path. So this lets you customize which modules you can import. So you can have a local set of modules that you prepend to this path, and they will get prioritized over built-in modules. So it works in a similar fashion as DLL loading process on Windows. Also, you can see additional linker arguments that you can pass here, or you can override a linker command entirely here, if the custom link command set to true, and other stuff like that. The point is that in Jai, you use Jai to compile your program. You can actually use Jai to compile your dependencies that are not written in Jai. So Jai has a module that's called run command, or here it is in the process module. You can just run external command, which will open a subshell in a cross-platform way. So if you're using some C dependencies that you want to recompile your build, you can do this without leaving Jai entirely. You don't need anything else on top of that. You don't need any weird shell scripts. You don't need any of that. So you might have noticed me pre-typing this message loop. So what's that? In Jai, when compiler compiles your program, it actually runs an event loop internally that you can plug into and listen for compiler messages to do interesting stuff with the code. And in order to do this, you need to start intercepting these messages before you add your first file. So compiler begin intercept with a workspace. And here, somewhere here, you call your message loop. Again, you can do it in line. I just do it for better indentation in the file because font is big. And at the end, you run compiler and intercept. And here you just run a while loop. So while true. And inside of this loop, you poll compiler for messages. So message equals to compiler, wait for message. Here you don't need to provide workspace anymore because now the compiler knows which workspace you're interested in. And after that, you are switch casing on the message kind. So if message kind equals, and this is a syntax for Jai's if case. So which messages are there? Let's check it out. So let's go to compiler, and at the very end, here's our message. And here are all the kinds that compiler exposed. So we have file for when file is getting added to the workspace, just like we added our main. Import for when module gets import. Failed import, so you can potentially remap it. We have multiple phases. We have a message for type checked. We have a message when everything is done. Error, performance report, and debug dump. And then phase has also a few types it can be. So a bit here down below, message phase can be of these types. So we have a phase when all the source code is parsed. We have a phase when we type checked all we can. It's called like that because it can fire actually multiple times. So you have an ability to insert code into the target program while it compiles. And so the compiler will type check all it can. You can insert more code. The compiler will have to parse and type check it again. And then it will call this phase one more time. And this will happen as many times as you keep inserting new code. And as well, all target code is built, and then pre and post write your executable. And here is the one for customizing linker command. So you can see it's very, very granular. And if we go back, So the simplest one is probably case complete. Yeah, complete. In this case, all we need to do is just break out of the loop. And the most interesting one that we'll probably want to do is type checked. So type checked, yeah. And in Jai, cases breaking by default, so you don't need to do anything specifically, but if you want to fall through, you just need to invoke a directive through, like that, just for completeness sake. I'm not gonna do it. So inside of this case, we need to cast our message. So type checked is cast pointer to message of message. And then let's probably have another helper function to reduce the indentation, handle type checked, and we pass in the message. And handle type checked will be somewhere down below, and it will accept a pointer to message type checked, just like this, and it's not gonna return anything. So now let's address the main technical bit of question that I got on my previous video. A lot of people had questions about this syntax. To be specific, the fact that you don't always have to specify a type here. So Jai has automatic type inference. It's something like auto keyword in modern C and C++. And so a lot of people said that, oh, this is too confusing. I wish this, like doing this or that, right, or that, would be mandatory. And I responded to multiple comments like that, oh, you can actually customize it. You can make it mandatory if you want. And then I decided so many people asked this, so I gotta make a video about it, right? And so this is what we're gonna do right now. We're gonna create a house rule or so-called linter by using compiler message loop to check all of the type check messages and see if any of them have implicit inference. And we will produce a compiler error if we detect that. Just like linter in any programming language, but just using built-in Jai compiler module because it provides everything we need. So if we go and look at message type check definition, which is in the compiler module, we can see that it contains a bunch of stuff separated by the type of the code. And we are going to be interested in the code procedure body. So this type check struct wraps the particular code node in the expression field. And so this is why we need to iterate over PB, so procedure bodies of message procedure bodies. And we need to extract the body itself from the expression, so PB expression. And if we go to the definition of code procedure body, here's the struct. It has a block on it, so the code block and also the header. And if we go to our main, so code block will be everything between square brackets, and procedure header will be this part with the name of the procedure and its signature. And so for the sake of the simplicity, we will be only checking our main function. In a real linter, you would want to separate your own code from the third-party code, and you only want to check your own code. And in Jai, you can easily do this by checking on each code node this field, location. It has information about file where it comes from, so you can separate it like that. But we will do the easy thing here, and we get a procedure header. It comes from body header, and simply if header name not equals main, we will just continue looping until we get to the main. And also, as I said, we need our block, so just call it body block. So now each block contains an array of statements besides all other things, and each statement is a code node. And logically enough, each statement is this line that ends with a semicolon. And for now, let's just loop over them. So for statement block statements, so let's just print the statement. And since it is a pointer to code nodes, let's dereference the struct and let's actually call it. I haven't called it in a while. So what do we have here? Compiler and intercept. It accepts the workspace, and yes, so now we have a bunch of stuff here, and there's a lot of noise. So let's actually reduce the noise. Default Metaprogram has a quiet flag, and what quiet flag does, it just sets a thing on the options that's called text output flags. It just sets it to 0, and if we rerun, yeah, here it is, it's much clearer. So our main contains procedure call and 3 declarations. And fair enough, in main you can see a procedure call to print and 1, 2, 3 declaration. So that's our guys. And let's actually print them in a nicer way so we can see every struct field. And in Jai, you can control how different types are printed by using a special control struct. So in our case, here we're printing the struct, it's called format struct. Just like that, it is a helper. And if you provide 1 here and true here and rerun it, you can see that now struct is getting printed much nicer. So what are these magical numbers and booleans? Good question. So let's quickly check it out. It's in the basic print and it just says how many members the struct needs to have to use a long form. So we want to use long form always, and also use new lines if long form, we just set it to true. And this is our format struct. It's just a bunch of stuff that controls how the struct getting printed. For example, what separator to use between the name and the value. It's pretty self-explanatory. And so we don't have to do it every time. Let's, I guess, extract it into something like PS. So PS print struct, which will accept any type. So I guess let's just call it generic T. Jai has generics. And let's extract print over here. And it's gonna call format struct on S. And you don't even need to dereference the struct because Jai will automatically do it for us. And here we can call now just PS on our statement. And this should just work, and it does. So procedure call, declaration, declaration, and declaration. Nice. So our goal is to ban implicit type inference in the declarations, so we need to only look at them. And the way you do it is just you check the kind of a code node. So if statement kind not equals declaration, what we do, we just continue. And if it is, we need to cast a generic code node, which is a statement to a particular kind. So decl equals to cast code declaration of statement. Jai also has compound declarations. So it's stuff like A, B, C equals foo, because Jai has multiple returns. We're not gonna deal with this. It's actually the same thing as declaration, but it's nested. So a compound declaration will just contain multiple inner declarations that we need to recurse into. That's about it. I just wanted to mention that these exist as well. So yeah, we get our code declaration from the statement. And let's actually print our declarations and see which fields they have. So declarations have an entry, which is the base code node. You can even see here name. So we have A, B, and foo. Here they are. And they have a bunch of stuff. Namely, they have type instantiation and they also have expression. And both of them are filled with something. If we go back to our compiler module and we go to code declaration here. So type instantiation is the A thing. So the type is type instantiation. And expression is B, so this thing. So if we remove A, type instantiation will be set to null. If we remove B, expression will be set to null. So if we go to main, this is type instantiation. If we remove them, they will be set to null. So here, you can see that type instantiations exist, but if we run our program, we can see that now they set to null, just like I said. So let's actually go to main and create a few of them more. Let's make it a string, and let's also create C that's gonna be just S64. And then we go to build and recompile. And so we need to have one of these where type instantiation set, but expression is not set. And it's gonna be our C. So you clearly see all of the cases. And let's think about how do we ban implicit inferences? Well, we can just check if type instantiation is null. And if it's null, we can complain. So let's actually do this. So here, if decl type inst equals to null, what are we gonna do? Well, let's just compile a report. So compiler report is a way to produce a compiler error, so like a custom compiler error. And we can just say something like implicit dereference found. And if we run this, it will abort our compilation, implicit dereference found. So you can see in Workspace 2, and if we click it, we go back here, which is, it's not super descriptive, right? So first, we need to know exact lines and characters and files where implicit dereference happened. And second of all, we probably want to report all of them at once, because this is what good linters usually do. So let's, instead of doing this, collect all of the inference into an array, and then we will report them when we see a message of the face type checked all we can. So let's do this. All right, so we need to create an array, and let's call it inferences. It's going to be a dynamic array, so this is a syntax in Jai for dynamic arrays. This is going to be an array view, so just pointer to a data and count. And this is the same thing, but it also contains an information about an allocator and current capacity. So it's your typical dynamic array. And it's going to be an array of pointers to code declaration, just like that. And if we detected this, what we're going to do, we just call array add on this array inferences, and we're going to add a declaration to this. So during the whole duration of the compile loop, these pointers will remain valid. That's why you can safely add them to an array, and then in a separate phase, you can report them. So how do you do this? You need to handle a separate kind of message. Let's call it case, it's face, if you remember. And then you need to do it a bit nested. So message face equals to, well, we need to cast our generic message to message face. And then if message face equals type checked all we can. This is the one. And then we just check if arrays count more than 0. We just report it here. And by the way, in Jai you can do the same thing as in Python. You can just do this if inferences. And the Boolean operator that works on array, it is smart enough to know that we mean to check the count. But I'm just kind of old-fashioned. I like it explicitly, even though I programmed in Python for 10 years. For some reason, in systems programming languages, I tend to be more explicit when I check stuff like nulls and counts. I don't know, just my thing. Anyway, so let's print some nice error. Let's print. And by the way, you might have noticed that I'm using print. I'm just doing it out of laziness, right? Here we're using log error. It will print to std error. And I'm just using print because it's easier to type. Just wanted to point it out. So the error message will be something like detected this amount of type inferences and something like explicit type is required. Exclamation mark. And inferences count. Let's actually rebuild it and see if we screwed it up. Yes, this is a typo. It should be face, and other than that, it's fine. Detected 3 type inferences. Good. So let's actually remove a print from here, and then we need to print each individual one. So how do we do it? We can loop over the array. So for inferences, and for funsies, let's not assign an alias this time. So every time I wrote a for loop, I assigned an alias here. So PB, so I can use it here. But by default, if you don't do it, if you just type for an array or some other data structures as well, Jai will assign default alias to it and it index. So as you remember, every code node has information about where it is on the file. And so you can extract this location by calling a helper that's called make location, which is also in user space. You can look up its source code. It just literally extracts the location from the struct. So we can call it on it. And after that, you can print this location, print, and you can print a file name, line, then comma, character name, another colon, and then some message and its location. It's called source code location. Let me look it up. It's in preload module and it has fully pathed file name, line number, and character number. So yeah, let me copy this up. Location.this, location line number, and location character number. And then some error. Let's leave it empty for now and let's just check what we have. So look at this. detected 3 type inferences. Explicit type is required. Oh, I messed it up. I put an exclamation mark in the wrong spot. Let's run it. There you go. Detected, detected, detected. And look at this. Since we don't abort the compilation, we still get executable produced and we still run the program. So you can see that if you want, you can make these a warnings, right? And if you click now, because Emacs is configured to parse Jai errors, so if I click it, I can go to the definition of each individual one. This is very nice, right? And if I put an explicit type here and save it and recompile my program, look at this. Now I have only 2 of them. Nice. But you can see that this is kind of weird. I just have file indicators, but without anything. It would be cool if we could just have an actual statement here, actual declaration. And you can do this. In Jai, you can print a code node to text by using, again, one module that is shipped with the compiler, which source code you can see. It's called program print. So let's import it here. This is how you do it. The way you use it is you create a string builder. A string builder is something like linked list of strings that you can then combine into one string. The way you do it, you just call it print expression like this, and you pass it a pointer to a string builder and it. So it, in this case, if you remember, is a pointer to code declaration, and print expression accepts a code node and it will internally cast it and print all of the stuff from it. And then here at the end, instead of printing an empty string, you can print the string builder back to string. So builder to string, and you need to give it a pointer. And let's actually rearrange the file so it looks a bit nicer in a bigger font like this. So it's a bit nicer to look at. And if I call it, here we go. You have this one, b equals string without, and foo equals get foo. And if we go here and add everything here, right, and we recompile it, now we have only 1 of them. And for completeness sake, let's actually abort the compilation when our linter fails. So what we can do here, again, in the message phase, we can check if message phase equals to something like all target code build. We can just, again, check if inferences count is over 0. We can just compiler report, let's do it like this, and there warehouse rules violations. And if we run it, naturally we abort. There were house rules violations, and on top of that, we print exactly where they happen. So this is how you can implement this sort of linter that checks for implicit references. You might also kind of think, what if I cast a return type of a function to the type? So for example, let's say we have something like another struct like bar, right? And what if bar is a subtype of foo? So as means that bar can be casted to foo, because at the top it has all of the fields of foo. And let's say we have get bar here, and it's gonna return like a pointer to bar. And we just return heap allocated pointer to bar, so call new bar. And here, let's say it's like foo1 equals to get bar, and let's say we cast the return one to pointer to foo, right? This should be a valid code. We can cast pointer to bar to pointer to foo, but if we try to build it, we can see that there is an error here. Explicit inference found, even though we clearly see the type that we are casting to. In my opinion, if I were to implement a linter like that, I would allow this to pass. And we can actually get it pretty easier. We just need to add another condition here where we check that type instantiation is null. What do we need to add here? If you remember in the compiler module, so code declaration has an expression. So this one is B, and we can check that the expression is of type cast here, kind cast. So we just add and decal expression kind not equal to cast. That should do it. Nice. Now we have only one implicit inference of B, which is string. Pretty cool, right? I know in Jai you can do stuff like, you can actually put a run directive here, right? So you can do something like run type, and then this will like return foo. Right, just straight up return the type from a compile time function. And if you were to recompile this, at the moment you see our linter does not detect this because it just sees that there is a type instantiation. But if you want to catch stuff like that, I just wanted to mention it, you can actually recurse into type inst, just like we did for expression, and you can check that its kind is not directive run. And you can say something like directive run, please extract it, buddy. And it's gonna be all right. Yes, and of course, if we add string here and recompile our program, you can see that now it compiles cleanly, does not complain, and lets it run it. And so there it is, 20 lines of code with some scaffolding that you would probably have anyway if you use custom Metaprogram. And you have a pretty powerful linter. How about that? And you can even go further and you can extract this linter in a reusable piece called a Metaprogram plugin. Jai lets you do this. Jai lets you extract this part of the message in a separate structure, call it a plugin, and then you can run a program that does not even use a custom Metaprogram, but it still lets you plug these reusable loops as Metaprogram plugins. And the simplest possible example of that, just for the sake of demonstration, so let's actually compile main without our custom build. We just compile it as is. And you can see I'm not even running it. But if I compile Jai main and I add an auto run with a plus sign and I run it. Oh, sorry, you actually need to do it after the file. So plus auto run. Yeah, there you go. You will see this autorun running main, and then you can see hello Sailor Moon. So what autorun does, it runs its own message loop, and when the compiler produces an executable, it runs it in a cross-platform manner. So for example, you don't have to do this end main if your operating system doesn't have this kind of shell expansion, which is very comfortable. And you can extract your linter into the same Metaprogram plugin. And then you can plug multiple of them at the same time. If you don't use custom Metaprogram, you can just do it through command line like I showed you with a plus. If you use custom Metaprogram, you can invoke multiple plugins programmatically from your Metaprogram. Your choice. So there you have it. Hope this answers a lot of questions that I had on the previous video. Also, if you want more of this, I actually have a edited down recording of a stream where I implemented a similar linter that searches for implicit pointer dereferences. It's quite a bit more advanced than this one, so I'm gonna leave it in the video description. Thanks for watching, subscribe if you liked what you see. In the next video, I'm gonna return back to the C programming language land, and I will see you all there. Thank you.